Most engineering failures do not begin with a calculation error. They begin with an ambiguous sentence, an undefined obligation, a copied requirement, a missing operating condition, or a technical practice that nobody can apply without asking the author what it actually means. Writing an engineering technical practice is therefore not administrative work. It is engineering work. You are converting accumulated experience, design knowledge, operating lessons, failure history, procurement learning, construction feedback, and maintenance reality into instructions that another engineer can interpret, apply, and audit without depending on your personal explanation. A technically competent engineer can still produce a weak technical document. Subject knowledge is necessary, but it is not sufficient. The document must distinguish mandatory requirements from recommendations, separate engineering guidance from procurement conditions, explain the reason behind critical decisions, align with recognized industry standards, and provide a transparent route from general practice to project-specific specification. The objective is not to produce a large document. The objective is to produce a controlled engineering decision system. An engineering technical practice should exist only when it creates measurable engineering or business value. That value may come from preventing known failures, standardizing equipment selection, improving technical integrity, reducing unnecessary design variation, controlling lifecycle cost, capturing operating experience, or closing gaps that recognized industry standards do not adequately address. The final result should support facilities that are technically sound, fit for purpose, safe to operate, and economically sustainable throughout their operating life. Before writing a new practice, ask a direct question. Does a recognized industry standard already provide adequate guidance? If the answer is yes, use the industry standard. Do not rewrite it under a different document cover. Repetition creates maintenance burden, revision conflicts, and false confidence. A separate engineering technical practice is justified when the industry standard requires qualification, when additional selection guidance is needed, when operating experience has revealed a critical gap, or when no suitable industry standard exists. Your document should add engineering intelligence. It should not duplicate available text. The guidance should also be general enough to support different projects, regions, operating environments, and business applications. Project-specific variables should not be left as blank spaces inside the core document. Those variables belong in project addenda, data sheets, or supplemental specifications. The engineering technical practice establishes the stable engineering baseline. The project document adds the variables. A disciplined technical practice system separates 4 document functions: the preamble, the guidance on practice, the guidance on industry standard, and the data sheet. The preamble establishes category-wide context, administration, and document relationships. The guidance on practice explains how engineering work should be performed. It covers design, construction, installation, commissioning, inspection, testing, operation, and maintenance. The guidance on industry standard qualifies an industry standard or establishes procurement guidance for materials, equipment, and systems. The data sheet captures project-specific information, selected options, process conditions, equipment ratings, and other variables. The distinction between guidance on practice and guidance on industry standard is not cosmetic. It determines the audience, technical content, document structure, and contractual use. Use guidance on practice when the subject is primarily engineering, design, construction, installation, commissioning, operation, or maintenance, and no exception to an industry standard is required. Use guidance on industry standard when the document controls the purchase of materials, equipment, or systems. Also use guidance on industry standard when an industry standard exists but requires additions, deletions, replacements, or clarifications. Guidance on practice may reference an industry standard. Guidance on industry standard qualifies it. Guidance on practice helps the engineer decide what should be selected and why. Guidance on industry standard communicates the resulting technical requirements in a form that can support procurement. Guidance on practice is written for engineers, operators, maintainers, inspectors, and engineering contractors. It should not be issued directly to an equipment supplier as a purchasing specification. Guidance on industry standard can be issued with project supplemental requirements to the supplier because its content is structured around procurement and conformance. Mixing these two functions creates confused documents. Engineering philosophy becomes buried inside supplier requirements, while procurement obligations become scattered across narrative design guidance. The result is interpretation risk, contractual ambiguity, and uncontrolled deviation. A useful guidance on practice does more than state preferred solutions. It should help the user assess hazards, understand known failure modes, select materials and equipment, compare system alternatives, apply design rules, and recognize environmental or process limitations. It may include selection criteria, advantages, disadvantages, operating constraints, installation options, maintenance considerations, and lessons learned from previous facilities. It should identify areas requiring engineering attention rather than attempting to teach the entire underlying science. Theory belongs in an engineering technical practice only when the theory helps the user select an option, define a requirement, or understand a limitation. A technical practice is not a textbook. For example, the document does not need a long explanation of compressor thermodynamics. It may need to explain why a particular compressor configuration becomes unsuitable beyond a defined pressure ratio, gas composition, turn-down requirement, or operating envelope. The purpose of explanation is decision support. Guidance on practice must not eliminate engineering judgment. It must create a controlled framework within which engineering judgment can be exercised, justified, and documented. It must also avoid blocking new technology merely because the technology was not available when the document was written. Requirements should control performance, integrity, and risk wherever possible, rather than freezing one historical design solution. Guidance on industry standard should be read together with the applicable industry standard. Its clauses should clearly identify whether they add to, delete, replace, or clarify specific provisions. Where practical, its numbering should follow the structure of the referenced industry standard so users can compare both documents without searching through unrelated clauses. Do not repeat the original industry standard inside guidance on industry standard. Repetition creates revision risk. When the industry standard changes, duplicated text can become inconsistent while still appearing authoritative. Guidance on industry standards should contain only the organization-specific additions and qualifications required to achieve the intended engineering result. Where environmental or process conditions determine the requirement, state those conditions. Do not prescribe a material, coating, test, or equipment feature without defining the service conditions that justify it. A procurement requirement without its design basis can easily be applied to the wrong service. Where no suitable industry standard exists, guidance on industry standard may provide complete purchasing guidance. Even then, it should remain aligned with the associated guidance on practice because procurement requirements should originate from the engineering selection philosophy. Guidance on practice defines the decision framework. Guidance on industry standard defines the purchasing control. One of the strongest features of a well-written engineering technical practice is the deliberate separation of normative guidance from commentary. Guidance tells the user what is required, preferred, or permitted. Commentary explains why the guidance exists, what alternatives were considered, what conditions may justify a different choice, and how regional, operational, or process-specific experience affects application. This distinction matters because technical requirements often become project specifications and contractual obligations. Explanatory reasoning should not accidentally become an enforceable supplier requirement. Use commentary when the reason for a requirement is not obvious to a competent practicing engineer. Use commentary explain selection logic, document known failure experience, describe conditional alternatives, and identify circumstances requiring additional evaluation. Commentary can also record legitimate variations for a particular region, operating environment, process, or business application. Commentary should be located close to the relevant guidance so the user can understand the requirement while reading it. However, commentary intended for internal engineering decision-making should not be issued to suppliers as part of the procurement package. A practice without commentary may tell engineers what to do while preventing them from understanding when the requirement no longer fits. A practice containing only commentary may provide useful knowledge but no auditable control. You need both, but their compliance status must remain unmistakable. The words shall, should, may, can, and will are engineering control terms. They are not interchangeable writing preferences. Use shall for a mandatory requirement. Failure to comply requires an approved deviation or means that the design does not conform. Use should for a preferred solution. The recommendation represents established good practice, but another technically justified solution may be acceptable. Use may to express permission or an available option. Use can only to describe capability. Use will to describe a future action or information that the responsible organization will provide. Do not use must as a casual substitute for shall. Do not write should when you intend mandatory compliance. Do not use may when you mean technical capability. This verbal discipline directly affects auditability. Consider the statement, the shutdown valve should close on confirmed high pressure. Is the function mandatory or merely preferred? If the safety analysis depends on that action, the word should is dangerously weak. Now consider, the shutdown valve shall close within an appropriate time. The obligation is mandatory, but the performance criterion remains undefined. A stronger requirement states the required action, initiating condition, defined response time, and applicable operating basis. Precision requires both the correct compliance word and a measurable technical condition. A technical practice should contain front matter, numbered clauses, and, where needed, annexes. The scope is mandatory and should be brief. It should state what the document covers and may state what it excludes. The scope must not contain technical requirements. A statement such as, "This practice provides guidance for the selection and use of temperature instruments," is clear. A scope that includes design criteria, supplier obligations, and inspection requirements is no longer a scope. It is uncontrolled technical content placed in the wrong location. Normative references should be included only when the body of the document depends on them. References used merely for information should not silently create compliance obligations. Terms and definitions should be included only when specialized terms require controlled interpretation. Do not define ordinary dictionary words. Do not use a term inside its own definition. Do not mix definitions with requirements. Symbols and abbreviated terms should be listed separately where they are required. Units of measurement are not abbreviated terms and should not be listed as such. Each clause and subclause should have a title and a clear technical purpose. Numbering should progress continuously and logically. Do not create a single orphan subclause. If Clause 5.1 exists, Clause 5.2 should also exist. Otherwise, the additional subdivision adds complexity without improving navigation. Organize clauses according to the way engineers use the document. This may follow the engineering workflow, equipment life cycle, design sequence, or a progression from general requirements to specific requirements. Documentation requirements should be grouped under a documentation clause. Inspection and testing requirements should be grouped under an inspection and testing clause. Scattered obligations are easily missed during design reviews, supplier evaluations, and project assurance activities. Annexes should be used when guidance has restricted applicability, when large tables or figures would interrupt the document flow, or when informative material needs to be separated from the main requirements. Every annex should be identified as normative or informative. A normative annex contains requirements that affect compliance. An informative annex explains or supports the document but does not create mandatory obligations. This distinction must be explicit. Engineers should never have to guess whether an annex is enforceable. Notes and examples may clarify guidance, but they must not contain hidden requirements. Footnotes should be avoided because their compliance status is unclear and they are easily overlooked. If information matters enough to influence engineering compliance, place it in the body of the document. Writing style is not decoration. Writing style controls interpretation. Every statement should be accurate, brief, and comprehensible. Each numbered statement should address one subject. A requirement that contains several ideas separated by commas should usually be divided into separate statements. When one sentence contains design, inspection, documentation, and testing obligations, one of those obligations will eventually be overlooked. Use specific technical terms. Write centrifugal compressor rather than machine. Write control valve actuator rather than device. Write carbon steel piping rather than material. Consistency matters more than stylistic variety. Do not use 3 different terms for the same component merely to avoid repetition. In engineering documents, repetition of the correct term is safer than elegant variation. Avoid pronouns where the subject could become unclear. Words such as it, this, and those often force the reader to interpret which item the sentence controls. Avoid non-quantifiable language. Words such as adequate, robust, high quality, heavy duty, suitable, normal, readily available, and best practice sound authoritative but provide no measurable basis for compliance. Do not write, the enclosure shall be robust. State the mechanical load, environmental classification, corrosion resistance, ingress protection, or impact requirement. Do not write, the alarm shall be readily visible. State the required viewing distance, location, contrast, display size, or lighting condition. Do not write, care should be taken during installation. State the exact installation control, inspection hold point, torque limit, cleanliness requirement, or handling restriction. A statement that cannot be verified is not a strong engineering requirement. Conditional clauses also require discipline. Use if for a defined condition. Use when only for a time-dependent condition. Use where only for a location-dependent condition. Do not use these words interchangeably. Tables should be used when they present guidance more efficiently than several paragraphs. They are effective for selection criteria, service limits, material classes, design conditions, test requirements, and responsibility matrices. Figures should be used when a diagram, flowchart, or arrangement communicates the requirement more clearly than text. However, tables and figures should not repeat the same guidance already stated elsewhere. Repetition creates conflicting authorities when one part is revised and another part is not. Equations should define every variable, applicable unit, and limitation. Unit conversions should be controlled carefully, particularly where manufactured sizes, tolerances, fits, or equipment ratings are involved. A mathematically correct conversion can still create an impractical engineering requirement. Quantities should be presented using the designated system of units consistently. If both international system of units and customary units are required, the conversion method must be clear. A hard conversion selects a logical manufactured or practical size in the second unit system. A soft conversion applies a direct mathematical conversion. You must understand which method is appropriate. Converting a nominal pipe size, plate thickness, or manufactured tolerance as though it were a pure mathematical quantity can produce a requirement that no supplier can meet. Document control is another engineering risk. Engineering authors working in an electronic environment must know who holds document custody, which version is authoritative, who may edit the content, and how comments, revisions, and approvals are recorded. Uncontrolled copies, overwritten changes, and conflicting review versions can destroy the integrity of an otherwise sound document. Use the approved document template. Do not alter established styles merely to improve local appearance. Standard formatting supports controlled editing, automated contents generation, document comparison, and long-term maintenance. Before releasing an engineering technical practice, perform a disciplined technical review. Confirm that all source documents, lessons learned, and relevant graphics have been gathered. Confirm that recognized industry standards have been checked before creating new requirements. Confirm that the document type is correct. Confirm that guidance on practice does not contain procurement specifications. Confirm that guidance on industry standard does not become a general engineering textbook. Review every use of shall, should, may, can, and will. Search for non-quantifiable words. Search for undefined conditions. Search for repeated requirements. Search for commercial and administrative language that does not belong in the technical practice. Confirm that commentary has been separated from normative guidance. Confirm that the scope contains no requirements. Confirm that clause order follows a logical engineering sequence. Confirm that terminology remains consistent. Confirm that figures and tables do not repeat or contradict the text. Confirm that documentation, inspection, and testing requirements are located where users will expect to find them. Then ask the most important question. Can another competent engineer apply this document without calling the author for interpretation? If the answer is no, the document is not complete. A strong engineering technical practice does not merely preserve knowledge, it converts knowledge into repeatable decisions. It allows engineering authorities to approve deviations through a visible and auditable process rather than through informal exceptions. It allows project teams to create specifications without rewriting the engineering philosophy. It allows suppliers to understand procurement obligations without being burdened by internal commentary. It allows reviewers to distinguish mandatory requirements from recommendations. It allows future engineers to understand not only what the organization selected, but why the selection was made. That is the real standard. Do not measure the quality of a technical practice by page count, complexity, or the number of requirements. Measure it by clarity, applicability, technical integrity, auditability, and the quality of engineering decisions it produces. When the document is written correctly, it becomes more than guidance. It becomes a controlled bridge between industry knowledge, organizational experience, and project execution.